Hello gang, I'm Billy from TypeScript.com at readsscript.com. Let's talk about the script behind this animation. It's going to leave the website soon. Fancy or cool websites do not necessarily convert well. A few people asked how it's working underneath the hood, and this is what this video is about. Here it's built with Angular 17, and I wrote the entire script from scratch in TypeScript. Let's dive in. So the script does three main things. It prints out the slogan at the center of the canvas, it calculates and assigns the ball over the letters, and it interacts with the mouse to create some dynamic effects. So let's take things from the start. We initialize the canvas and we print the text. Let's comment this out. Right. We need to send the font size and style. Then we measure the text so we can center it. Here. So measuring the width is easy. We subtract the text width from the canvas width and we divide the result by 2. Here it is. However, calculating the height is a bit more complicated. We need to account both the height above the hanging baseline and below, and the descent below it. Once we have that, we add half of the canvas height and half the text height. Let's move on. Then we create the agents, the balls. Right. Let's do that. We create the agents only once in the beginning. Afterwards, we update their values continuously instead of recreating them 60 times per second to match the browser's frame rate. When this is done, we call the sketch function here. This function runs once and it keeps calling itself with a request animation frame, which naturally occurs at 60 frames per second. You might have noticed that I'm using an event listener to check if the font is loaded. We could have used a set timeout of say 250 milliseconds, but I prefer this method. If we were not to wait for the font to load, the default font will be used and the balls will be calculated based on that font. This happens even though everything is inside the DOM content loaded event listener here. Inside this function, we also check if the canvas and the context exists, otherwise we return early. By the way, here I'm grabbing the canvas element, and this is far from ideal. If you're using the script in production, you have to address that. I have defined two interfaces and a class. You might ask, what is an interface? Well, an interface is like a contract. In TypeScript, it primarily defines types, while in languages like PHP, it often focuses on method execution. In this script, I implemented the interface in the ball class to create an abstract representation of the ball object. I didn't want to visually create elements here. This is why I placed the code before DOM content loaded event. It doesn't interact with the canvas context. Of course, usually in TypeScript, the interfaces are on the top. One of the interfaces defines a vector with x and y coordinates. If you're unfamiliar with canvas coordinates, 0, 0 is located on the top left corner. I know that this is not a full definition of vector, since vectors usually have both magnitude and direction, but for this script, the ball interface serves this purpose. It stores the original position, the current position, and the velocity. All of those are vectors. If you prefer to think of the current property, here I call points as velocity and velocity as acceleration, this is up to you. I prefer this way. I separated the vector definition because it's also used in the mouse position tracking, and the idea of vector really occurs frequently throughout this script. The ball class initializes the object, sets the color, and defines the points. That's all the class does. Then I define an agents array here, which is essentially an array of balls. And then I create the agents. We loop through the canvas in steps of 3 times the ball diameter. We move along the x and y axis. In each iteration, we gather the pixel data, we sum them up, and we determine if a ball should be underneath. I think it makes sense, right? We also have a variable called rect, which is calling a method get bounding client rect on the canvas. This is an essential method to know if you're planning to work with canvas elements. It helps to rule out any areas outside the canvas when calculating the mouse position. So here we deduct left, which is basically this distance here, and top from y, which is basically this distance here. So how do we handle the mouse interaction? This is all the juice of the script is. Let's trace back to the sketch function right here. If the mouse is over the canvas, we need to calculate the distance between the mouse and each ball. I think there must be around 82 balls or so. To find the distance, we're using the Pythagorean theorem. Since we have 2 vectors, here's the very simple function. Since we have 2 vectors, we subtract the x and y coordinates to create a right triangle. The hypotenuse of that triangle is the distance we're looking for, which also serves as the magnitude of the vector. Let's have a look at the image visualizing that. Of course, here we're in Cartesian coordinates, so 0, 0 is here and not on the top left corner. If we know x1 and y1 and x2 and y2, which is, say, I don't know, here's the mouse and here's a ball, we can calculate these points, so therefore we can calculate a and b and c, essentially. I hope it's clear to people by now what a vector is representing here. The magnitude of the vector is proportional to the speed. We basically have a velocity as a vector with x and y values, calculate the distance from the mouse, and we update the velocity accordingly. We do that 60 times per second. The balls should move freely in all of the directions, right? In any way, in each direction, really. So that's why we need to calculate here direction x and y, and we do that here as well. So the values here can be potentially negative. Then we normalize the vector. Vector normalization reduces the magnitude to 1 while preserving its direction. Since the distance between the mouse and the balls is the magnitude, we reuse that value instead of recalculating it, then divide both x and y by this magnitude to normalize the vector. Here I'm assigning distance, I'm not recalculating because the distance is the magnitude. Right, let's have a look at the illustration here. In the same shape, this is the original vector, which is 5.83, and then we divide that, we divide b and a with that to find a little tiny vector, maybe here, that has the same direction, that's the size of 1. The direction x is this one and the direction y is this one, in case that was not obvious to people. Why do we need vector normalization? Well, without it, the balls would move inconsistently depending on their distance from the mouse. Let's see what would happen without the normalization and without any correction. So I'm not saying that this is not a cool thing to play and watch, but I hope by now you get the idea about normalization. Here I have a correction. basically the correction or the normalization. It's just like maintaining the direction of the vector, but is reducing it. And I'm using this method over the normalization when the balls are returning back to their place. Normalization ensures that all the balls move smoothly and proportionally to the mouse influence. And as I discussed, we're applying the correction method for the movement back, whether the mouse is over the canvas but far enough to interact, or is not even on the canvas. Vector normalization is a common practice in computer graphics, particularly in game development. Game development is not really my area of expertise, but I'd love to work on a game someday. You might have noticed that we're dividing the magnitude by 3 just to mitigate a little bit the effect of the normalization. Another interesting point that probably is not obvious to everyone is that vector values are defined as numbers because that's a native JavaScript type. However, these numbers are floating point values and not integers. Why does that matter? Well, sub-pixel calculations allow for smoother, more natural movement rather than the whole pixel increments. This is due to anti-aliasing and interpolation that is happening underneath the hood. Let's have a look how it looks when we round the points to integers. Let's go here, already prepared that. Hopefully TypeScript will not give us any more pain. Yeah, I think you get the idea. You might think that this happens because we initially set the ball position as float points instead of integer during their creation, but that's not the case, and I invite you to try. You should be aware that there are a lot of situations where sub-pixel rendering is not ideal. For instance, if you're placing images inside the canvas, sub-pixel calculation can hurt performance without providing any noticeable visual benefits. If you want to explore the code or play around it, check the description for a link to the GitHub repo. Let me do that because I will push the codes. Yeah. That's it for today. It was a supercharged tutorial. We talked about interfaces, TypeScript, events, vector, classes, vector normalization, the Pythagorean theorem, interpolation, anti-aliasing. Computers are fascinating, and so are the graphics. Stay tuned, I will be releasing an ebook soon. In the meantime, check out my websites because I'm gonna release a new version, so you can give me feedback. Feel free to comment if you have any questions or remarks. Maybe you can tell me what you want to see next. And thank you so much for watching.